Hello students, welcome to EduCat. In the chapter of chemical kinetics, in the previous classes, we have discussed about the basic concepts of the rate of reaction, the order of reaction, molecularity of reaction, integrated rate law equation, and the half-life period of a reaction. Now, in this video, we will discuss about temperature dependence of the rate of a reaction. That means, on increasing the temperature, the rate of reaction will increase or will decrease, or if will increase, then what will through what value, and if decrease through what value. Generally, on increasing the temperature, the rate of reaction increases, and for every 10 degrees Celsius rise in temperature, the rate of reaction becomes double. Why about that? We will discuss. So here already the concept is given that on increasing the temperature, the rate of reaction increases. Written here. Rate constant will become double, means rate of reaction will double, because R is equal to K, because you have already studied R equal to K, concentration of reactant in case of zero order reaction, R to the power 0, in case of first order reaction, K into R, in case of second order reaction, that will equal to K R square, that you have studied. So if rate constant will increase, rate of reaction will also increase. Okay, this one. And now about the rate of reaction that we studied by Arrhenius equation. We will now discuss Arrhenius equation. It was firstly proposed by Van 't Hoff factor, but he have not explained this one about the equations. So Arrhenius have explained about this equation. So that's why that is called Arrhenius equation. Now, what the Arrhenius equation states? Arrhenius equation states that for a chemical reaction, the temperature dependence will be that means rate of reaction, rate constant, that will be equal to K, the rate constant K, that will be equal to A e to the power minus EA upon RT. Here A is called Arrhenius constant, or that is also called frequency factor. R is called Arrhenius constant or frequency factor or pre-exponential factor That is, A is Arrhenius constant or frequency factor or pre-exponential factor. So K equal to, here given here the question, K equal to A e to the power minus EA upon RT. This equation has been given here. K equal to A e to the power minus EA upon RT. Now, how to simplify this one? K equal to A e to the power minus EA RT given here. E is natural exponent. E is here natural exponent. Now, how to derive the equation? Take log, natural log, because here it's natural exponent. So take firstly natural log. So log K, that will be equal to log A e to the power minus EA upon RT. Now you know already log A into B, that equal to log A plus log B. Same, log A upon B equal to log A minus log B. So here it is in the form of log A and into e to the power minus EA upon RT. So that's we can write. So that's why we can write log K equal to log A plus log e to the power minus EA upon RT, and log A to the power x equal to x log A. Okay, so log E will be equal to 1. So that's why here this one, so log K will be equal to log A minus EA upon RT log E. Log E is 1. So we can write log K will be equal to log A minus EA upon RT. Okay guys, very simple. Now let's see, at temperature T1 rate constant is K1, and at temperature T2 rate constant will be K2. So log K1 will be equal to log A minus EA upon RT1, and log K2 that will be equal to log A minus EA upon RT2. Now subtract this, we subtract this equation from this equation, this equation from this equation, or this equation upon that equation, whatever you would like. Okay, till here, that's the here, till here you may, if you would like, then you may write, otherwise in the books also that is given. So that is given here. We will discuss here why that happened. You watch out from here. There is. So we have already written log K1. We have already derived there log K1 equal to log A minus EA upon RT1, and log K2 will be equal to log A minus EA upon RT2. Now log K2 upon K1 we are discussing. We calculate log K2 upon K1. So log K2, we subtract this equation. That means this is equation 2, this is equation 1. So subtracting equation 2, subtracting equation 2 from 1. So what happened? Log K2 minus log K1, that will be equal to log A minus EA upon RT2 minus log A minus EA upon RT1. That will be equal to here same. So log K2, log A minus log B. I have taught you log A minus log B, that equal to log A upon B. So log K2 minus log K1, log K2 minus log K1, that will be equal to log K2 upon K1. So that will be equal to here log A minus EA upon RT2 minus log A plus EA upon RT2, that's upon RT1. This one log A, that will get cancelled out. So log K2 upon K1, that will equal to here EA upon RT1 minus EA upon RT2. EA upon R can be taken as common. So log K2 by K1, that will equal to EA upon R, 1 upon T1 minus 1 upon T2. Now when we will have to convert the natural log into log to the base 10, we will have to multiply by, here this one is natural log, we will have to convert this natural log into log to the base 10. So then we will have to multiply this one by 2.303. So we can write 2.303 log K2 by K1. That will be equal to EA upon R, and here very simple, LCM of T1 and T2 will be T1 T2. When you divide T1 T2 by T1, that will be T2. So here T2 into 1, this one, that will equal to T2 minus same way T1 T2 divided by T2, so that will be T1 into 1, this one, so that will be T1, this one. So that is here log K2 by K1, that will equal to EA upon 2.303 R into T2 minus T1 upon T1 T2. This equation. Okay, that may check here also. So that's the formula here. Okay, that is. Now that was what actually is on increasing the temperature. When we increase the temperature, then what will be the effect on the rate of reaction? That was here. But more important here is why on increasing the temperature, the rate of reaction increases. Watch out about this graph, and this one is very important about this one. Okay. A hypothetical reaction is here seen hydrogen and iodine that react with HI. Here, this is the molecule of H2. So bonding between the atoms of hydrogen atom, and there is bonding between hydrogen atom and that of this hydrogen atom. In the same way, that H2 is reacting with I2 and there is formation of 2HI. This equation when we discuss. So this is the hydrogen molecule, this is iodine molecule. So when they collide, when hydrogen molecule and the iodine molecule collide, then this hydrogen molecule, this iodine molecule, there will be some bond formation between this hydrogen and this iodine atom, and between this hydrogen and this iodine atom. That means bonding between this hydrogen and this iodine will take place, and as well as between this hydrogen and this iodine, and there will be weakening of this bond as well as this bond, that will get weakened. So here between this hydrogen and this hydrogen, bond will strengthen. There will be a strengthening of bond between this hydrogen and this iodine, as well as between this hydrogen and this iodine, and there will be cleavage of bond will start from here. So finally this bond and this bond both will dissociate, and bonds between this hydrogen atom and this iodine atom will take place. So that's why when bonding between this hydrogen and this iodine take place, so this HI molecule, same here this HI molecule. This stage at which there is bond formation begins between hydrogen and iodine atom, and that of this hydrogen and this iodine atom, and the dissociation of bonds between these two hydrogen and that of between these two iodine starts. That stage is called intermediate stage or intermediate complex, or that is also called, this one intermediate is forming. That means during a chemical reaction, the species formed whose half-life period is very small, that is called intermediate. During the reaction, the species which forms for a short time period, that is called intermediate. It is unstable, and it is also called activated complex. Okay. So activated complex here. So what is here activated complex? This is the energy of reactant. This is the energy of reactant. Potential energy of reactant. This is potential energy of reactant. How you calculate? From this to this one. This is the graph of potential energy versus reaction coordinate. It is the graph of potential energy versus reaction coordinate. So when we will have to find out the potential energy of reactant, so goes on the graph, this one is the potential energy of reactant. This is the energy of activated complex, that means this one. This one is the potential energy of activated complex. So what happened? How much energy we will have to supply? Because reactant have already some energy. Total activation energy, total energy of activated complex will be from this one to this one. This one is the energy of activated complex, and this is the energy of reactant. So how much extra energy we will have to supply to form the activated complex? So this value till here to here, total energy of activated complex, and from here to here, that is the total energy of reactant. So that much energy we will have to supply. So this one here, so that's why this difference of this energy, this energy and this energy, that means the total energy of activated complex minus the energy of reactant, that will be activation energy. So activation energy is the minimum amount of energy which must be supplied to the reactant to make its energy equal to activation energy. The minimum amount of energy which must be supplied to the reactant to form the activated complex, that is called activation energy. This is activation energy, the minimum amount of energy which must be supplied to the reactant to form activated complex is called activation energy. Okay. One point also keep in the mind. In this case, the energy of reactant is that much and the energy of product is that much. So difference of this energy, this energy will release. In this case, the energy of product is lower than that of reactant. So the rest amount of energy will release. If graph will be like this, this is of reactant and this is of product. So this is the energy of reactant and this will be the energy of product. So this value of energy will absorb by the reactant to form the product. So activation energy will be that much from here to here, that will be activation energy. Energy of activated complex will be from here to here. From here to here will be the energy of activated complex, and activation energy will be from this reactant to this activated complex, that will be activation energy. This is the energy of reactant and this one is the energy of product. So rest amount of energy that will be absorbed during the reaction. So when the energy of product will be lower than that of reactant, when the energy of product will be here in this case, when the energy of product will be lower than reactant, then the difference of energy, that means energy of product minus energy of reactant, that will be absorbed during the reaction. While when the energy of reactant of product will be less than that of reactant, here energy of product will be less than reactant, then the difference of this energy will release during the reaction. So here when the energy of product will be lower than the energy of reactant, then the reaction will be exothermic. While when the energy of product will be lower than that of reactant, then the reaction will be endothermic. Okay. So what happens when we supply the energy goes on this graph. One point here come about the most probable kinetic energy. I think you are aware about most probable velocity of gases. Most as was the most probable velocity, same is the most probable kinetic energy. So most probable velocity was the velocity possessed by maximum gaseous molecule. That was most probable velocity. The velocity possessed by maximum gaseous molecules was called most probable velocity. In the same way, the kinetic energy possessed by maximum molecules, maximum reactants, that will be called most probable kinetic energy. The energy possessed by maximum reactant molecules, that will be called most probable kinetic energy. Okay, so what happened here in this graph here is fraction of molecules. Fraction of molecules here is increasing. Fraction of molecules here is increasing. This side, fraction of molecules, and this side, kinetic energy. So fraction of molecules like this one here, then after fraction of molecules here, and at this point the fraction of molecules is greatest. Fraction of molecules is greatest at the peak, this one. Then after, the fraction of molecules again starts decreasing. So this one here is maximum fraction is this one, and their kinetic energy is that much. So most probable kinetic energy will be this value. This value will be most probable kinetic energy. This value will be most probable kinetic energy. Okay. So what is here on increasing the temperature? The most probable kinetic energy of reactants increases. That's why on increasing the temperature, the maximum molecules, that means molecules having kinetic energy greater than activation energy, the energy of reactant, the energy of greater number of reactant molecules will become equal to activation energy. That's why on increasing the temperature, the rate of reaction increases. Let's see about this graph. Here, this is the graph of fraction of molecules this side and kinetic energy this side. So this is the graph of reactant molecules. This graph. This is the graph of the reaction at T. At T, this is the graph. Okay. Threshold activation energy here. At increasing the temperature, the activation energy on increasing the temperature, the number of molecules having energy greater than activation energy or equal to activation energy become more. That's why on increasing the temperature, the rate of reaction increases. On increasing the temperature, the rate of reaction increases because the number of molecules having energy equal to or greater than activation energy. That's why on increasing the temperature, the rate of reaction increases. So in this case, this is the graph of fraction of molecules and their energy, kinetic energy. So these molecules, that means from this area will represent the molecules having energy. That much molecules will have energy greater than activation energy. That much molecule will have energy greater than activation energy. Okay, and in the next point, we take at T equal to 1 plus at temperature, when we increase the temperature through 10 degrees Celsius. So new temperature will become T plus 10, and their graph is this one. This is the graph when the temperature has been increased through 10 degrees Celsius. So this is the graph here. Watch out here. Fraction of molecules, that means most probable kinetic energy that has been is less. So this is the area from here to here, this whole area. That means these molecules, this is the number of molecules here. This one will be total number of molecules whose energy will be greater than activation energy. And you watch out that now you may watch out this area whole from here to here. This area is twice of this area. This area is twice of this area. So that's the reason for every 10 degrees Celsius rise in temperature, the molecules having energy greater than activation energy becomes double. That's why for 10 degrees Celsius rise in temperature, the rate of reaction becomes double. Okay, we have plotted the graph. Here this equation we have derived, and now we just consider about this graph. You already know here you have studied here derived log K equal to minus E upon RT plus log A. So you can also write log K will be equal to log A minus EA upon RT. That means when you will plot the graph of log K versus 1 by T, when you will plot log K versus 1 by T, so intercept will be log A, and that graph will be a decreasing graph, of which the intercept will be log A and the slope will be minus EA upon R. That is here slope is minus EA upon R and intercept is log A. 1 by T, when we go from left to right, 1 by T is increasing. That means temperature is decreasing. So on decreasing the temperature, the value of log K is decreasing. That means on increasing the temperature, the value of log K will increase. That means the rate constant will increase on increasing the temperature. So don't be confused. This is the graph of 1 by T and not T. So as we have plotted the graph of log K versus 1 by T, then this graph is a decreasing graph, of which the intercept will be log A and the slope will be minus EA upon R. Okay, now let's see here. Now proceed. We have solved that questions here. We have solved this experiment, this derivation. Now let's see solved this question. This is given rate constant at 500 Kelvin and at 700 Kelvin has been given, and it is asking the value of activation energy and the Arrhenius constant. Okay, so this one is very simple. You have already studied and that's given in the book. So from here I am telling where you need my help, special help, there I shall teach you. Log K2 by K1 equal to EA upon 2.303 R into T2 minus T1 upon T1 T2. That we have discussed already. We have derived here. Same above formula. So log K2 is here taken K2 0.07. So K1 will be 0.02. So T2 will be 700 Kelvin and T1 will be 500 Kelvin. So that has been, data has been put in. That's why log 0.07 upon 0.02, that will be equal to activation energy upon 2.303 R, this one into here T2 700 minus T1 500, 700 minus 500 upon 700 into 500. So that's you calculated here. EA 0.5, this one calculate. So 7 upon 2, that will be 3.5. You will have to watch out in log table. You can write 3.50. So in the log table, from this side, there will be 10, 11, 12, 13. Until here, you comes at 35. Come here at 35. This one. And 3.50. So there will be 0, 1, 2, 3, 4 until 9 here. So you will have to watch out 0 of 35 here, this value. So what will be the value? That value, put a decimal after that value. So that will be 0.544. There was 544 in the log table. You watch out. In the log table, 0 of 35 will be 544. So put a decimal after the digit. So 0.544. This one equal to here, that has been calculated. This calculated value, this calculated value. So E upon after calculation, this calculation, that become this one. So 5.7 this one. Then after this, activation energy this upon this. You have to calculate, very easy it is. Now how to calculate this one? I think a number of students will feel difficulty how to calculate this one. So how to calculate the value of Arrhenius constant? So Arrhenius constant, you know, log K1 will be equal to log K1 or K equal to A e to the power minus EA upon RT. So take log K1, that will equal to log A minus EA upon RT1. Put value here, log K1, or if you want to take log K2, so then in case of log K2 here also, then you will have to take log K2 equal to log A minus EA upon RT2. So among these two, either you put the formula in this equation or in this one. Same procedure there will be. So take here log. So log K1 equal to log A minus EA upon RT1. So EA upon RT1, that will be equal to this EA upon RT will when go through this side. So EA upon RT1, that will be equal to log K minus log A minus log K1. EA upon RT1 you calculate. EA given here, activation energy given here, this much. So 18230.8. R is 8.314. Temperature here is T1 you have taken, so 500 Kelvin here. That will be equal to log A minus log K1. So log, so directly I am putting here. So log A minus log K, so that will be equal to log A upon K1. Now put here, convert it to log to the base 10. So 18230.8 will upon 8.314 into 500. That will be equal to 2.303 log A upon K1. So now log a upon k1, log a upon k1, that will equal to 18230.8 upon 8.314 into 500 into 2.303. Calculate this one whole. Okay, you have to calculate, and then after k also you find out. So that will be log a minus log k. That will equal, calculate this one, and that will equal to this value 18230.8 upon 8.314 into 500 into 2.30. This one. Okay guys, firstly watch out how that I did. That is equal to here 4.38. This calculate, and log k here, log k is here 0.02. So log a will be equal to, log a will be minus log 0.02. That will be equal to 18230.8 upon 8.314 into 500 into 2.303. Okay. So let's see how to find out this one. So log a minus here log 2 into 10 power minus 2. That will be equal to 18230.8 upon 8.314 into 500 into 2.303. Simple calculation it is here, nothing more. So that will be here 2. So log a here minus 2 and minus 2 plus 2 minus log 2 will be 0.301, 0.301. That will be equal to here. This calculation is 1.904. When you will calculate this one, 1.904 will be there. And log 2 and minus 0.301. So log A plus 1.699 equal to 1.904. So log A equal to 1.904, 1.699. Zero point 205. So A will be here 0.205 will be equal to anti-log 0.205, and remaining you calculate by yourself. Okay, so in this manner, that is the process by which you can solve this question. Okay, don't we get frustrated. What you will have to do, this one here, take log both sides, and then after you convert them log to the base e to the log to the base 10. Okay, so this is the method how to solve second portion of the question, that is how to find out Arrhenius factor. Now let's see second question. What the second question is? A first order rate constant for the decomposition of ethyl iodide by the reaction this one at 600 Kelvin is this much. Order of reaction is given for decomposition ethyl iodide by reaction this one at 600 Kelvin is this much. Its energy of activation energy this much. Rate constant at this one given. So simple here, put the formula, get the result, log K2 minus log K1, this one. So simple here, this was very simple, put the formula, get the result. Log K2 minus log K1 equal to E upon 2.303 R 1 upon T1, this one you already know. Or you also know log K2 upon K1. So you know log K2 upon K1, that equal to TA upon 2.303 upon R T2 minus T1 upon T1 T2. That's you already know. So by that, putting this formula in this formula, you can very easily calculate. And as a result, that has been given. K2 will be how much? That means at 700 Kelvin, T2 will be 700 Kelvin, and T1 will be 600 Kelvin. Activation energy is given already. R, the value of R, universal gas constant, you already know. You have put in the formula and have got the result. Okay guys, this question was very easy, not? Okay, now in the next video, we will discuss about effect of catalyst. What will be, that is, what is catalyst, about that we will also discuss, and chemical collision theory of reaction, about that we will discuss here. In addition to that, we will also discuss about some important questions, numerical questions of the exercise. Some numerical questions, few. Okay, so it's all for that this class. In the next class, we will discuss here about the effect of catalyst and collision theory of the chemical kinetics, and some important numericals. Okay, it's all for this class. Thank you, Team Educate.